Okay, today we're going to look at some problems from section 2.3 in our textbook, techniques of differentiation. And prior to today, we've been finding the derivative and slopes of tangent lines using the limit process. So today we're going to start using some of our rules or techniques of differentiation. So let's just review. We have the constant rule, which says the derivative with respect to x of the constant c is 0. We have the power, which is what we'll use most often, which says the derivative with respect to x of x raised to the nth power, where a is a rational number, is n times x raised to the n minus 1. We then have the scalar multiple, which says the derivative of c times f of x is equal to c times the derivative of f of x. Moving on, we have the sum difference. And that rule says that the derivative of the sum or difference of two or more functions is equal to the derivative of each, and then we can take the sum difference. The next two, the product and quotient, are a little trickier. So for the product, if we have f of x times g of x, so that's equal to f prime of x times g of x plus, then we have g prime of x times f of x. And again, the order doesn't matter because we're adding there. And then finally, for now, we have our quotient. And here we'll do f of x divided by g of x. And so that's equal to g of x times f prime of x minus, so the order certainly here matters. Then we would have f of x times g prime of x, and all of that is divided by g of x squared. So here's the basic rules that we're going to be applying today. Maybe lower that one a little bit there. Okay. All right, so let's go through a couple of examples. I think we've got about 8 or 9 that we're going to look at. Okay, so here we start off and we have y equals 3x to the 4/3. So we're going to do both our scalar and our power, because 4/3 is a rational number. And so we're y equals, so we have y prime equals 3. And then the derivative of x to the 4/3 is 4/3 x to the 4/3 minus 1. And some of this in here you're going to do fairly quickly, and maybe not write all of this out, because you'll take 4/3 times 3, which is what we're going to do here, and the 3's divide out. And we get 4, and then 4/3 minus 1. 1 can be written as 3/3, so we get 1/3. And I think very quickly you should be able to go from here right to there. Okay, and we'll show you that doing it here. So we have f prime of x, let's see, are we fully, there we go, is equal to the derivative here, 2 times 2, we have 4 to the x to the first, because n minus 1, 2 minus 1. Here we would have 4, and then x to the 1 minus 1, or 0, or just 4. Down here we have another polynomial. Here we're using g, and again the variable doesn't change it, so we have g prime of t. So 1/3 times 12, so that's 4t, and 1/3 minus 1 is negative 2/3, minus the derivative of 2t is 2, and then the derivative of the constant 1 would just be 0. And here, number 4, what we want to do is write this in power form, which means that we're going to write it as x to the 1/2. So now, in applying our power rule, we have 1/2 x 1/2 minus 1 is minus 1/2, and you can certainly leave it like that, or you could write it as 1/2 times the square root of x. And I'm sure that looks familiar to you, right? We've had others, problems where we've done y equals root x using the limit process. Okay, let's look at a few more. So here we have the product of two functions, and you see I have it twice. I'm going to show you two different ways to do it. The first is we're going to apply the power rule, or product rule rather. So it doesn't matter which one we do first. So I'm going to take the derivative of x squared plus 1, which is 2x plus 0, plus, so now I'm going to take the derivative of 2x minus 1, which would be 2 minus 0. Right, so there's our, in essence, f prime times g, g prime times f. And look what happens when we distribute 4x squared minus 2x plus 2x squared plus 2, and we have 6x squared minus 2x plus 2. Now the other option you have is you could distribute, and you would end up with 2x squared minus, 2x cubed, and then you'd have a minus x squared plus 2x minus 1. So now if I take the derivative, 3 times 2 we get 6x, 3 minus 1 is 2. Here we get a minus 4x, or minus 2x rather, because we have 2 times 1, plus 2. And notice the exact same derivative either way. So it's up to you. As these get a little bit more complicated and a little bit bigger with powers, and you'll see we'll do something with the power rule later on, usually probably easier to keep it in here than to distribute. All right, so here what we have is a composite function. So you have a function x squared plus 4 being raised to a power, so you could write this as a composite. And we have a special rule called the chain rule that we've not covered yet. So I'm going to show you, for now, what are we able to do. And so the only thing we can do at this point with the rules that we have is to expand this. So in expanded form, we have x to the 4th plus 8x squared plus 16. And so our derivative, f prime of x, we end up with 4x to the 3rd plus, and then 2 times 8, 16x to the 1st, and then plus 0, because the derivative of 16 is 0. Now we move on, and we have a quotient, rather. And because we're in y equals, we'll have y prime equals. So I always like to start by, I know that we have the denominator first times the derivative of the numerator. And so the derivative of the numerator, the derivative of x squared is 2x, and then with the derivative of 2x is 2, the derivative constant 0, now minus, so then I have the numerator, and the derivative of the denominator is just going to be 1, all of that divided by the denominator squared. So there's really all the calculus. The rest of this now is going to be algebra. So here I will distribute, and we end up with 2x squared. That's an 8x and a 2x, so that's a 10x plus 8. And because I'm going to subtract here a trinomial, I like to use parentheses so that I don't lose track of my signs and subtracting. So 2x squared minus x squared is x squared. 10x minus 2x is 8x. And 8 minus 1 is 7. And from here, we do want to see if we have any factors in common. I can tell we don't, but just so we know, if we do try to factor in the numerator, we end up with x plus 1 and x plus 7. So that really doesn't help us. If we left our answer in that form, we'd be fine. But you always want to make sure that there isn't some factor in common that we could divide out. Okay, and let's look at just one more problem. So here, notice we have g of x equals 3x plus 1 raised to the negative 2. So again, we have a composite function. The negative tells us to take the reciprocal, so rewriting this, we have 1 over 3x plus 1 squared. And again, we would have to apply a chain rule, which you'll learn soon, which we would do here. But because we don't have that yet, we're going to expand the denominator, and we have 9x squared plus 6x plus 1. And so now we're going to have to apply the quotient rule. So we have the denominator times the derivative of the numerator, and the derivative of a constant is 0, minus the numerator times the derivative of the denominator. And so we have 18x plus 6. And then the denominator squared. So rather than leave it here, I'm going to go back to there. And that was 3x plus 1 squared. And we're going to square that. And you'll see why in a minute here. So we have g prime of x. So 0 times anything is 0. So distributing the negative, or actually, we can distribute. So we get negative 18x minus 6, and the denominator 3x plus 1 to the 4th, because squared is to the 4th. So remember earlier we did talk about seeing if there's anything in common that we can divide out. So if I factor a negative 3 or negative 6 out rather, because 6 divides into 18 and 6 evenly, look what we're left with, 3x plus 1, and then the denominator 3x plus 1 to the 4th. So notice I do have that factor in common that we had talked about in our previous problem. So when we divide that out, we're left with to the 3rd power in the denominator. And so our derivative here would be negative 6 divided by 3x plus 1 to the 3rd. All right, so I hope that helps you out. This is just our introduction, obviously, to derivatives using some of our different rules. You will get lots of practice. See you soon.